to the organizers for inviting me, and also to Professor Anđelković. Closer to the mic.
I'll turn it on.
Okay, better? So thanks again for inviting me. Today, I'm coming as a speaker after the pioneers and masters in this field, so my presentation will be a little bit more humble than previous three, but at the university we are trying to implement indoor air quality, and basically we are trying to develop an indoor environmental quality platform. We are currently at the state that they are finishing the prototype for basically a sensor node. So basically, okay, as as the previous presenters have mentioned, that we spend a lot of time indoors, basically like 90%, and even in like endangered, let's say, minorities, like elderly people in hospitals and infants spend even 100% of their time indoors. So we have to, let's say, improve the quality in our buildings, and especially in Serbia, where we even have lower standards than what is broadly acceptable. So we are trying to, let's say, be pioneers here and basically teach people that not only temperature and relative humidity influence their well-being and living inside of the buildings. So basically I will not talk about the building syndrome, this was mentioned here before. As a definition for indoor environmental quality, it's basically a set of parameters that describe general climatic conditions necessary for well-being and comfort of people inside the buildings. And basically, you have heard that there are a lot of parameters that influence indoor environmental quality, but we have stuck to those that we can basically measure with a sensor node. And basically, like Professor Rogotsky stated, we have like four different categories: thermal comfort, indoor air quality, indoor lighting, and noise acoustic performance. And basically, thermal comfort is a subjective state of mind, but we have basically a thermal environment which has its physical and chemical parameters, and we can measure them. And there are a few let's say, methods to perceive whether the occupants are thermally comfortable or not. So basically, we stuck to measuring dry bulb temperature inside of the rooms, relative humidity, mean radiant temperature, and air movement for thermal comfort. Now, for indoor air quality, there is a lot of basically organic and inorganic gases that can be measured: vapors, particulate matter, and microorganisms. We will see later what we have chose to measure, and we can measure light intensity and also noise and acoustic levels inside rooms. So as a platform, we basically wanted to have nodes placed around the building that all collect and aggregate data and send it wirelessly, basically on the client through Internet of Things services. The data would be aggregated there, and maybe a decision-making process should be triggered, basically. And of course, we can, for instance, in the sensor that we use, we can do the data aggregation in themselves and let's say, make it easier for the cloud to process the data and inform the user of the, let's say, real-time improvements that they can make in their indoor environment. So basically, these are the, let's say, necessary steps. So signal measurement, communication with the cloud, and in the cloud we have aggregation, processing, and let's say we have some response. So let's say for the user that can open the window or integrate with, let's say, BMS systems to make automated responses for the users. So for the platform itself, we stuck to Arduino as it is really become developed in the past couple of years, and there is a lot of knowledge base that we can already access, and the mass production is sufficient for mass production basically of the sensor nodes, and we can also have off the market or the market acceptable sensors connected to the microcontrollers, but not always easy with Arduino, as only the best boards from them have the capability basically to store a lot of data and process a lot of data that these sensors send to the microcontrollers. And basically, for instance, we had a lot of the problems since the sensors use a lot of energy for heating elements. None of the boards could supply enough of energy themselves, so we had to then go and find another basically voltage regulators, because the sensors work on different voltages. Also for prototyping, it's really good because you don't need to wire or solder anything. There are breadboards, and basically you just stick the connections in the breadboard and to the microcontrollers and sensors, and you can then basically try different combinations of sensors. So for the thermal comfort, we are currently using, so there is not a lot of sensors commercially available for let's say, air velocity. The best one that we could find currently is the wind sensor P, but even that sensor is basically giving us only one-dimensional measuring on the wind speed, so we will try to develop our own sensor that can give us the estimate of air velocity in all 3 dimensions. And also there is a lot of inaccuracy in this wind sensor, as it is basically meant to measure wind, not the draft that we have indoors. Also for the basically other let's say thermal comfort parameters, we are using environment combo breakout. So basically these are 2 sensors combined on one board. One measures TVOC and CO2, and basically other one measures temperature and humidity. So basically they are put together because then the one sensor sends the temperature and humidity data to the other sensor, and basically we get less, let's say, or more accuracy. But we have found out, because the other sensor is heating itself up to measure TVOC and CO2, it disturbs the measurements of the other. So there is a lot of inaccuracy and a lot of calibration needs to be done. So basically it's better if they're even split. For the black globe temperature sensor, there is no commercially available sensor, but it's really easy to make thermometer. It's around $25 to make it. You can use any thermistor and you can measure the temperature, and you can see that we have a discrepancy of, let's say, 0.5 Celsius to the measuring equipment commercially available that we used. For indoor air quality, we are using, let's say, like 6 sensors. And the first sensor for particulate matter, we are using sharp sensor, optical dust sensor, and basically here we also have some problems because the sensor cannot distinguish between PM10 and PM2.5 particles. It basically measures any particles to 0.5 micrometers. But there are some also tricks that we can use to distinguish PM2 and PM10 particulate matter. For instance, for smoke, tobacco smoke, the particles are more dense, and basically the output signal that we get is more consistent. And when the dust falls through the optical basically hole, we get peaks because the dust particles are much larger, and we can then distinguish what are one and the other. Another, let's say, trick that we use for determining the indoor air quality in regards to let's say, chemical components is that there are readily available MQ sensors, and this is the list of the sensors that we use. but also these sensors are not that accurate, but they can give a really good estimation. So basically, if the threshold is let's say, met, then we can send a user a command that he should open a window or leave a room, but not the let's say, true parameter or true ppm of those matter that is in the room. But this is basically, we have electrochemical sensors that are used for these types of measurements. Also for noise and ambient light, we use sound detector. This is the best one available currently on the market, and this also presents a problem as this sensor gives an amplitude, not let's say the pressure in decibels. So we had to make basically our own calculation to get the pressure. Basically, we had to calibrate it in a very quiet room and then get the bottom half of the amplitude, and then basically comparing it to the commercial available device, then we get what is the air pressure in decibels. Also, we have an ambient light sensor, which is really accurate. It's currently being used in mobile phones. And basically, we had a lot of good experience with this sensor. We also, of course, calibrated, it's very small on the screen. We used the test equipment and we calibrated a lot of our sensors in our laboratory. For the connectivity, there is a lot of options with Arduino to connect it to the internet. For the first phase of prototyping, we always use, let's say, wire transfer, and basically the Arduino software that you program in also gives you a serial monitor that you can monitor the parameters. But it's really hard to transfer this data to, let's say, Excel or some other softwares. But for the first starting, let's say, couple of iterations, it's really good. But it limits our mobility, and we cannot test without basically a PC. It's really clunky. Of course, there is options to integrate with SD cards. We also have a micro SD card. So basically, it's really reliable and secure. And basically, you congregate all the data that you have gathered. Because the files are really small, it's basically unlimited storage space. Also, let's say, we cannot get the data in real time, so basically we have to take the SD card to our PC and then transfer it, so we cannot see the data in real time. Also, we have used the Wi-Fi module, and basically we get great mobility, we get full independence from PC, and we can connect multiple basically nodes to one IoT server, and we can get data simultaneously. Also, let's say cons are, it's really unreliable. Basically, if you lose connection, you will not get any data. So that's why we combine basically Wi-Fi and SD card reading. And we have also GSM abilities, but it can be really expensive, and basically depends also on your provider whether you can lose connection. So basically, for the first start for the wire, you can see from the Arduino IDE itself, it's a little bit small, but these are the parameters. And there is a lot of freeware software, basically, so you can integrate the microcontroller with Excel, and you can, in later stages, directly store your data to Excel for examination. So as for IoT connections, basically how we managed to do it, there is in the, let's say, last couple of years, a lot of commercial platforms have become commercially available, and these are some that offer basically their IoT connections, and we had opted for Blink as it is really user-friendly, gives a lot of tutorials, and basically with someone who has who doesn't have a lot of knowledge with programming can basically connect to their servers, and they have a great app which you can also customize to whatever you like. So basically how we do it, we connect Arduino to the Wi-Fi module, but also it is not so easy to connect it. It's not like plug and play. You also have to program the Wi-Fi module as it can be as a microcontroller itself, and it has different basically firmware on it. So the process for programming the microcontroller is a little bit tough. So then the microcontroller or the ESP1S connects to the Blink server, and the Blink server sends the data directly to app. I wanted to show you how the app looks like on the phone. You don't even need to have a PC. So basically these were measurements that were done yesterday in around half past 10. So basically I connected it in my hotel room, as I wanted to do it live here, but it's not a really good place. And this is basically me blowing in the sensor, so you can see the drastic increase, and the measurements are sent to the servers at interval of 1 second. I don't know where it stopped. But basically all the parameters that are shown here are also shown as bars here, and basically you can send reports to your PC at any time that you like, and make the reports as you like them. So it's really a flexible system. You can send commands, you can turn off the units, turn them on, and so on. So basically this is the first, let's say, prototype. It has the shape of ASHRAE logo because ASHRAE helped a lot in funding this project. And for the project itself, the logo is a little bit covering the total price. But this is some estimated price with the retail value of the sensors of the sensor node itself. And basically we wanted to make it low budget. We wanted to teach people about indoor environment quality, and we wanted to, let's say, present them some graphs that they can understand even without the knowledge, deep knowledge about the environment quality. So basically it's around $225, but in the next stages there is also a lot of software that can help you basically prototype your, let's say, nodes. And you can see that here we have a software that basically in virtual environment lets you connect nodes with sensors. There is like currently trend with Revit and BIM. You have a lot of libraries with commercially available equipment. Here as well you have a lot of commercially available equipment, and you can make even schematics and transfer your basically whole concepts on the PCB and make it smaller. So we think it's too large now, but we will make it smaller. So basically that will be all for the current state of our project, but I would like to let's make let's say a segue that when we started doing this project, I was rummaging in our laboratory for some thermocouples to start measuring temperature, and I found a black suitcase. I didn't know what it was. I took it out. It was like around 15 to 16 kilograms. And when I opened it, we found that it's Confitest EQ21. It's from 1976. It has never been used in our laboratory. And inside we found Funger's first book of thermal comfort that was in English language. So it basically comes from DTU. And you could have seen on the top video that it fully functions. The only problem, so basically you start with the temperature humidity measurements, then find the vapor pressure. With that vapor pressure, so the third knob, you set the vapor pressure, and then with the level of loading and activity, you can basically determine the thermal comfort. So it still works. It has never been used. Only problem is the relative humidity as the marker has dried up. So we have to fix that. So thank you for your attention. Thank you.